All right. Hello, everyone. So today we are honored to have um, Uduna uh, join us. Uduna is an assistant professor in the Department of Neurology and Neurosurgery at McGill. Um, she's also a member of the Neuroimaging and Neuroinformatics Research Group. And so today she's done a lot of work on building capacity around artificial intelligence. She famously has led some training programs in Africa called Spark. And this is really important in terms of as we enter the era of artificial intelligence, the importance of building local capacity. Um, and so today, we are really delighted to have you, Udona. So I'll hand over to you.
Thank you so much. Can you guys hear me very well?
Yes, we can.
Okay, just give me 1 second. Let me just set up my load up my slides. Just give me 1 quick second. Let's just see here what we have. Uh, um, nope, not this one. Just make sure I have the right one queued up here. Mm, okay. Just, can you see my slide? Is that
Not yet.
not yet? Oh, okay, hold on. Let's see. I always, when I switch from Teams to Zoom, it's always yeah, so just sorry. 1 second. Let's see. Um, um, okay. Um, Try this one here. Can you see it? Still not showing? Is it showing?
Not yet.
Not yet. Okay. Uh-oh. All right. So let's just, maybe I'm not showing the whole. Should take it off Canva. Okay, 1 second. Let's try this again. Try showing. Oh, is that the right one? 1 second. Try this. Okay, try this now. Um, anyway, well, I'm always sorry. Well, just give me one
No problem. Yeah.
second.
Take your time.
Mm. I did team classes for a bit now, so going back to Zoom is always. Is that the right one? Nope. Maybe I should get rid of this screen. Um, is that the right one? Okay. Nope. I don't think this is showing. Let's try this here. Okay, let me try now. Okay, I'm just gonna. Okay, so I'm just gonna go desktop. I think that will make it work now. Yes, I see myself and I think you guys have seen this.
Yeah. You just need to
Yeah,
put.
okay. And
Perfect.
I'll get rid of this. Okay,
Yeah. Yeah.
fantastic. And then
Excellent.
let me find my laser pointer. Okay. So thank you so much for inviting me. And I'm super happy to share a little bit of some of the work we're doing to implement AI in healthcare settings. This is the title I was given, is to implement AI in healthcare settings. But for me, I've been trying to do this within one particular healthcare setting, which is the African healthcare setting. And some people might call that healthcare setting a resource constrained, low and middle income country settings, LMIC setting. I think that that fits all of those disclaimers or all of those descriptors. And I think I'm going to use this to sort of talk a little bit more about how we can learn from the Africa healthcare setting to implement AI across all healthcare settings. And that's because if we kind of look at this from a healthcare implementation in a resource, let's just say abundant setting or a setting like the US or Canada, where I am typically based, a lot of the resources, a lot of the challenges and healthcare issues that we have are not readily transferable to resource-constrained low-income countries or African healthcare settings. But I think there's a lot that can be translated in the reverse. So this is sometimes called reverse innovation that could go from the African healthcare setting to a resource abundant or resource like a high income country setting. And that's because we can do a lot more with little in a low resource setting, and we can learn a lot from doing more with little in our US or whatever healthcare setting. So that's kind of the what I wanted to talk about today. And this is kind of new. This came to my attention. This was a LinkedIn post. This is how I found out about it, because this article is still on paywall by New York Times. I mean, they're talking about the global AI divide. The article is pointing out where all the AI data centers are. You can see that the ones, any of the data centers, and this is the Amazon one, the Microsoft Azure, or even the Google one, they're all based in South Africa, in Africa, for example. And you can see that there's a huge loss of opportunity in terms of access to data centers across the rest of the continent and also in many other low resource settings. But Africa is actually one of the ones, places that have the most in terms of gap in access to data centers. And this is really, I mean, I'm happy that this is coming to the attention of the regular, what I call it, everyday community. So this is New York Times. This is not Science or Nature, or any of those papers. So this is now coming to the consciousness of everyday people. But back in 2022, we started to talk about this divide, at least within radiology, within medical imaging, which is what I do, about this need to democratize access or make sure that AI can be available, applicable, and implemented in all healthcare settings, especially within low resource or resource constrained settings. And the take home message from here, and what we've known, at least for quite a while, is that AI does have the potential to really transform and improve population health outcomes. This is across all areas of health care needs. So this is both in oncology, in neurology, in any aspect, pediatric aspect of healthcare where radiology has a need and a use. We know that AI can actually improve outcomes there, and it's more likely to do that in low resource settings because of the potential of AI to close gaps in personnel. So, for example, being able to create rapid diagnostic tools or prognostic tools with artificial intelligence tools that will augment the limited number of trained personnel. That's one example of even being able to optimize their current infrastructure. So being able, for example, in radiology, in what we do, there's now a lot of AI methods that have been introduced that can help improve the image resolution or the contrast to noise ratio. So the ability for us to see lesions well. So for example, if you're looking at oncology cases with AI, even with the suboptimal or lower resource setting equipment that we have. So we've known this for a while, right? And a good example of this, how AI is now, dominating and becoming quite everyday tool in, at least again, I'm going to use radiology as an example, but this is across all healthcare settings, is something as rare in a certain sense as brain tumor. So brain tumors are not, in terms of all tumors, these are one of the rare forms of cancer. And even within that, there are now quite a lot of AI companies that have been FDA approved and cleared, including ClearPoint Maestro, which is now something that Philips, one of the major distributors of medical imaging device, or medical device in general, they've now adopted and pushing and selling some of these softwares. These are all softwares, AI softwares that are now allowing radiologists and also oncologists, especially those that are doing tumor planning or doing diagnostics, to use some of these softwares to augment their practice. So AI is becoming part and parcel of healthcare across many different settings. And the reason for this is, again, I'm going to use brain tumor to illustrate how we've gotten this far and fast, to a certain extent, not far, but fast, with AI implementation in healthcare settings, especially again with something as rare as brain tumors. If this is happening in brain tumor, you can imagine that this is happening in every other typical stroke, breast cancer, all of those very typical or more common, I should say, healthcare outcomes. You can imagine that whatever I'm saying right now is happening as well in these particular healthcare issues. So one of the reasons why some of these health AI softwares are becoming quite routine is that a lot of these softwares, and again, I'm going to use radiology. I believe that this is one of the areas where AI has made a much deeper penetration in health, in a healthcare setting or in healthcare disciplines, is radiology, is that we've been able, with at least within the international radiology community or medical imaging community, have been able to start to develop the softwares or develop tools that will lead towards the softwares decades and decades ago. So brain tumor, again, an example of this is there have been an international effort to provide data sets. So for brain tumor, MRI typically is the routine and standard of practice modality that is used in order to detect, classify, characterize, and also do tumor treatment planning. So there's been an effort for the past 10 years. This is through the Brain Tumor Segmentation Challenge, which is run by the Medical Image Computing Computer Assisted Intervention Society, the MICI Society. They've been running this challenge for over more than a decade, since 2012, where they provide, and this is by institutions that have come together and given, I mean, like I say, publicly available or open access data sets that have been annotated or well defined. So each of those cases have been characterized by a trained expert, typically a clinician, the radiologist, and the radiologist, that have gone ahead and created this ground truth data set so that when these data sets are released publicly, openly, people can use that to create deep learning methods that can now automatically segment the tumor subtypes, the tumor subclasses, which allows you to do some characterization of the tumor, quickly assess the tumor volume, for example, and also be able to even predict to a certain extent what type of tumor it is, glioma, meningioma, and also, which is classified, and also even start to do some prediction for treatment outcomes, especially when you have post-therapy data sets. So this has been going on for over a decade now. And this systematic review, a meta-analysis, sort of illustrates how much of a progress has been made in the field with this particular data set. This is a paper that looked at 224 studies that have used deep learning or machine learning to either do automatic segmentation, to segment them into the tumor subclasses, or do prediction and also classification. So being able to figure out which one is glioma, meningioma, and the rest. The summary here is that essentially over the past 10 years. So this paper came out in 2022. So this is a 10-year outlook on what has been happening with this particular data set, is that the methods are getting as good as a expert radiologist. And so this is why some of these softwares are actually, a lot of these softwares are actually built up on some of these public data sets because they have been benchmarked, they have been validated, in the sense that we have the data sets are made available with a training data set, they're made available with a evaluation data set, and they made it available with a testing data set. So there's a way to actually do external and internal validation with whatever methods have been developed. Now, the question is when it comes to now applying this particular tools, let's just say the best performing tools that are publicly available, because every year when the challenge is done, the tools are that are the methods that have been proposed publicly are ranked in terms of performance, using metrics, including DICE scores and all of that stuff. And so we know which methods are performing very, very well, which ones that can handle what the tasks are much better. And some of these have made their way into softwares. Some of these are like NVIDIA. NVIDIA has a public available tool that people can download and use that have been created by them and have been part of the Brain Tumor Segmentation Challenge for years. And people sometimes use it as their base model to further fine tune and further fine tune and develop other methods from. The question is, if we take some of these methods, these data sets obviously came from the West. A lot of these data sets came from Western institutions, because that was essentially how a lot of these challenges start. There's not a lot of participation from LMICs for many reasons, which I'll talk about in a second. So we wanted to know, my lab wanted to know, this is what Dong Zhang did when he was a master's student in my lab. We wanted to know if we take some of these top performing methods, including those that have been developed for stroke segmentation. So there are methods that have obviously similar things also happening in stroke with the ILS challenge, ischemic lesion segmentation challenge, same thing with BRATS. They provide data sets for stroke, ischemic stroke, and people use those data sets to create methods. This I7s have been running for practically the same time as BRATS for over a decade. So we wanted to take some of these methods and just say, okay, well, let's just see how well it works on African data sets. So data sets that come from African healthcare settings. So this is an example from three cases. Where in these cases, I think one of them is ischemic stroke. I don't remember which one it is now, and neither two are glioma cases or example of glioma cases. And we wanted to just run these models through the data sets. I mean, they should be able to segment them. I mean, an MRI is an MRI, an image is an image. Why is it that they're not able to segment these images? So you can see that when you run it through some of these top performing models, that they don't perform quite well. The DICE scores are quite low. Some of them are, horrendous. But then when we decide to take these data sets and include them in our training data sets and build our own model, a model is a very simple CNN model, not sophisticated. But one thing we did was we wanted to make sure the model pays attention to some of the nuances and typical nuances, and you're going to see what those nuances in a second, that are dominant and quite common in African healthcare settings in terms of image quality, some other things I'll show you in a second. We find that our model performs much better than some of this very sophisticated top of the line or state of the art model. And that's just only because, and I think this is common sense, that we all know that now. It's if you don't include the data sets, you don't capture their features and some of the challenges, you're not going to build a model that's able to, at least in this particular case, when it comes to lesion segmentation, segment the lesions or even identify them very well. And the reason for that is some of these data sets that are used to create a lot of these AI applications that are that are sort of propagating over all healthcare settings, including LMIC or African healthcare settings, is that they come from places that have really rich and many data sets. And here again, to illustrate this with the brain tumor segmentation or even the stroke segmentation challenge tasks. These are the typical images that are part of the public data sets that have been used for over a decade in creating some of these top of the line or state of the art AI models. These data sets tend to be high resolution, meaning that they are finer and thinner sliced images. So they also have multiple different type of contrasts. So they have rich information. So you have a T1 weighted, a T2 weighted, a flare, post contrast, even diffusion weighted imaging. So these are available. And we have thousands and thousands of cases to use in developing and training and evaluating the models. And when you come down to a African healthcare setting, which is not only African, this is common in 80% of the world because a lot of places in the world don't have the type of MRI or imaging infrastructure as we have in the West. That's one. Second, they don't even have any. A lot of places don't even have an MRI. A lot of countries in Africa don't have an MRI scanner to begin with. And so you find that there is now this huge gap and huge disparity, meaning that this is a standard clinical setting in Africa, where for brain tumor imaging, we have thicker slices that sometimes they get to be 6 millimeters thick. So they're quite lower resolution, they're quite coarse images. Sometimes you don't even have contrast because contrast agents are quite expensive and sometimes not even available. Some of them don't even have the ability to do diffusion weighted imaging on the scanners. And so you have less information to train and characterize and capture that particular task, in this case, lesion segmentation or characterization of a lesion. And there's very few cases because healthcare is expensive. Imaging is very expensive to begin with. In Africa, healthcare is a private setting. There's no public healthcare in many places, and even if there is, most of these are not subsidized, or imaging is not subsidized or covered under any resemblance of a public healthcare system. And also, patients show up late with delayed and more complicated presenting problems. So when they come in for imaging, their case have progressed. And you can see that also on the MRI, that the images are now more complex, or the tumors present more complex than the ones from high-income countries where patients show up much earlier. And also, there are a lot more information to characterize the tumors with in African healthcare system. For example, we don't do a lot of biopsies or any pathology confirmation. Some of that is not even available. So you have this high quality, plenty shot, plenty information, rich, plenty data sets, more veracity compared to the low risk setting, or the African setting. And so this is why most of these current methods that are state of the art, some of them making their way into software applications that are intended to be used in healthcare settings or implemented in healthcare settings, do not work very well when you bring it down to everyday settings, what I call everyday setting, because this is what a typical setting is in most parts of the world. So the question is, how do we start to solve that? Because initially, when we started this discussion, we talked about the fact that we know that AI has the potential to be the equalizer, meaning that it could improve healthcare outcomes in low risk settings or in all settings around the world. So how do we actually make sure that that happens? What are the barriers to implementation of AI in low risk settings? I want to use low risk settings because if you solve that problem in low risk settings, you solve the problem in everywhere. So AI becomes implementable across all settings. One is infrastructure. Second is personnel capacity and the availability of skilled and trained personnel. And the other one is policy. And we've sort of categorized this into these three different categories because this is based on our experience trying to implement and bring AI to healthcare settings in Africa. And so I'm going to quickly just kind of go through this. The infrastructure, a lot of this may have been covered in what I said. A lot of the healthcare settings in Africa don't even have an MRI scanner. When they do, it's typically low field, so low resolution. It produces a lot less resolution than a typical standard clinical MRI scanners in the West. Same thing goes for PET, for example, positron emission tomography, which is a bread and butter for oncology imaging. A lot of places don't have a PET scanner. I mean, the PET scan, there's only one PET scan in Nigeria, for example. There's a lot of countries, I think the entire continent or subcontinent of Africa, there's maybe about 8 PET CT currently in operation in the entire continent. So you can see that there is this infrastructural gap and need. And so if you don't have the infrastructure, you don't have the data, you cannot be able to train or include the data sets in models or methods that have been developed and with intention of being deployed or implemented. There's all of these issues, including the lack of computational hardware. We started off by showing that AI divide where there's no data center in anywhere in Africa except South Africa. And just the issue with network connectivity, because that's going to be a big issue with being able to deploy models, run models, or even be able to participate in some of these, what I call it, crowdsource. So some of these challenges that produce data sets and then people come together and build models. Well, a lot of these data sets are in cloud. If you don't have the ability to download them or even run some of your models, even if there are some cloud-based computing infrastructure, that becomes a huge barrier. Skilled personnel is just a given. There's a lot of personnel that are required to implement AI, from the clinicians that are able to diagnose the conditions well, trained on how to even understand what AI is doing, even trained on how to develop the AI methods in informatics, the medical physicists, I'm using imaging here as an example again, the competition scientists. There's just a big lack of expertise all around in from being able to provide a data set for training, being able to even understand how to develop the methods, or even optimize methods that have been developed or adapt methods that have been developed to this healthcare setting, and also being able to even deploy or evaluate or validate those models. Policy, again, is a huge issue. There's lack of sufficient data privacy and protection all around. Healthcare in Africa, especially in imaging, is in the private sector, meaning that you have private practices that run a lot of these very expensive medical imaging devices, including oncology treatment. A lot of the cancer treatment centers are private practices. They're not in government hospitals or academic centers. So when it comes to research, these people are business minded. So bringing research into a private practice, some of these are mom and pop private practices, becomes a little bit of a barrier because there's some of them don't have an ethics. They don't have an ethics board, for example, for you to start to do some of this research translation and funding. I think that's a given. Most of you are probably aware of this, that healthcare funding in Africa in general is well below what the UN or what the World Health Organization standards or requirements are. And it's even more lower for healthcare research and non-existent for healthcare research that requires you to use imaging, very expensive imaging data sets or very expensive imaging methods in general. So this is a huge barrier, and how do we overcome that barrier? And so this is when I'm going to start to transition to what we've done in Africa, especially within Nigeria, to start to overcome some of these barriers and move towards implementation of AI in African settings, in low resource settings that can be translated back into high income settings or across the whole world. So I'm going to use this project that we were funded to do in 2020. This is the African Neuroimaging Archive. It's a very simple project. The idea when the funding we got from the Lacuna Fund was for us to aggregate imaging data sets, make it publicly available for people to use that to create methods that will be beneficial to African settings, because by making the data sets available, they're well curated, they're well annotated. Those data sets can make their way into models that have been developed and eventually will be deployed into clinical setting. So the idea is to start from data. If you make the data sets available, you start to make inclusion of models being developed and applicable in this African setting. So that was the main aim of the grant. But we, being Africans, again, like I said, we know how to do more with little. So we decided, well, for us, we just cannot bring a bunch of data sets together and make it publicly available. We really have to start to address some of these fundamental barriers, infrastructure, policy, personnel barriers. So with this one particular project, we've been able to create this ecosystem that allows us to go from policy, make sure the policy on the ground, the ability for us to do this research is there, ability for us to train people are there, and those trained people and infrastructure can be optimized to now be able to make rich data sets available, but also have the people on the ground that are trained on how to collect the data, how to annotate the data, how to use the data to build models, and then how to also deploy that data into deploy the tools developed with that data into healthcare settings. And that's what we've done with AFNU. So for time's sake, I'm just going to quickly illustrate some of the outcomes that came out of AFNIR from policy to personnel to infrastructure. With this grant, we were able to partner with a radiology practice in Lagos, Crestwood Radiology, run by Dr. Abiy Fatidin. He had about 5 clinics. One of those clinics have an MRI scanner, which we latched onto, and with partnership with him, he gave us access to his clinic. So we opened up a computational imaging lab called Medical Artificial Intelligence Lab, my lab, in his clinic. This is one of the rooms. Across the room is the blood lab. And if you go down this hallway, there's a seminar room here. Down the stairs, that's when the 1.5T is. The back door here is a server room. So he gave us generosity the space, which you can see has for now we have these 2 high-performance computers. These have been upgraded. The lab opened up in October of 2022. And we are also able to have a space where people can come and train. And like I said, there's a seminar room across 60 people. From that seminar room, we've been running the Spark, so the Sprint AI training for African medical imaging and knowledge translation program since 2023. And this is a hub. From there, we've been training and creating similar spaces across Africa to train quite a bit of people. I'm going to talk about this in a second. And from this lab space, we've been able to curate brain imaging. So this is where archiving all of those, brain MRI and brain CT. So these are previously acquired clinical data sets that we're putting together, using that now to build solutions. One of the ones that we did was quickly partner with the BRATS data set, BRAT's segmentation challenge to provide this data set and include African data sets and models that are now being proposed and developed. So now when these models become tools that are going to be FDA approved eventually, we'll be able to make sure that these tools have been trained on African data sets and can do what they are supposed to do, which is segment or plan or prognostics or whatever the case is. But the data sets are there and can be made publicly available for use. So with this brain tumor segmentation challenge data sets, this is just one particular individual showing that we were able to provide data sets comparable. I mean, the resolution, as you can see, it's not as good as the standard Western brain BRATS data set, but they're good enough for us to now start to create methods that can see, understand, segment, classify, and quantify the tumors just as good as you can do with the African data, with the non-African data sets or with the high-income data sets. We've run this challenge since 2023. We're running it right now in 2025. So the challenge is ongoing right now, but this is from the 2023 challenges. We had about 298 people that submitted methods. There are 38 teams, 154 participants from 21 countries in the world. 13 of those 21 countries are from Africa. And I want to tell you how we're able to get African people to participate for the first time in this challenge, meaning that they were able to take the data sets that we brought from Africa and develop methods from teams that are based in Africa that have, including clinicians, quite a few of them were radiologists or radiology residents they understand the challenges, understand the clinical setting, and we're able to develop a really what I call it, state-of-the-art or top-performing models. One of those models came out of South Africa. This is from 2023. This model was ranked the second highest in terms of performance. And so this is the first year that we train people on how to, build deep learning methods for brain tumor segmentation. And one of those teams that we trained participated in the challenge and actually did very well in the challenge. The data sets are now publicly available. Anybody can go in and download them. They are actually for 2024, they're one of the top downloaded data set in the National Cancer Archive, National Cancer Imaging Archive, so the TCIA NIH archive system would archive cancer imaging data sets. The Brain Tumor Segmentation Challenge data set was the #1 data set that was downloaded last year. And the paper that describes the data set, how it was curated, processed, and annotated, it's out there. So and everybody can actually go ahead and make use of that data set. I mentioned the fact that we're able to train or get people from 13 countries in Africa to participate at least in the 2023 challenge and the 2024 challenge. And that's because we were also solving one problem that is a barrier, which is that skilled personnel. So we created this Spark Train Academy to train experts where they are in Africa to take their current infrastructure that produces those images I showed you. They're a little bit low resolution, a few data sets, so sometimes missing decision-weighted imaging, and also that are not a lot of data sets. We wanted to train them to work within that particular constraint to optimize your clinical imaging infrastructure and environment. I wanted to make them work together in a collaborative network because if they do start to work in a collaborative network coming from multiple different countries, they're able to make use of that small data set. Imagine pulling data sets together from multiple different places, but also learning from the African healthcare system that is not one healthcare system. It's very independent, it's very different from as we move across countries. That will actually allow us to make sure that when we're developing these methods, we're developing methods that are robust and can be implemented across many different healthcare centers across Africa. The only way we can do that is by making sure that people work together in a collaborative network. So for Spark, what we did is actually our goal was essentially take ex people that are essentially willing to learn. So these include clinicians. We have trained radiology residents, oncology residents, neurosurgery. We had people from neurosurgery that have participated in the past. We've trained undergraduate computer science students, undergraduate physics students, undergraduate electronic engineering students, undergraduate neuroscience students. So anybody that is willing to learn, we have created a program that actually takes them from a trainee to a trainer. We use this three-step process, this teach, try, use, systematically taking them through a process where they learn everything about medical imaging with this specific use case application, which is brain tumor segmentation. So they learn about MRI and MRI physics from understanding what these imaging data sets are, like what a T1 weighted imaging, what a T2 weighted imaging is, what the features mean when you see them in a brain tumor MRI data set. We had radiologists come in and teach them how they read. So they're trying to understand how a radiologist sees these images to be able to create methods that can augment that particular radiology practice. We were able to teach them how to code, how to create data sets, how to augment data sets, how to process them. So we go through this very intense 6 to 8 weeks teaching course-based, very didactic lecture like teach phase. Once we give them that basic foundation knowledge, making sure that everybody's on the same field, because some people come in with deep coding skills. Some people come in, for example, radiology residents come in understanding what MRI is, obviously the radiology residents, but want to make sure that when we leave this phase, everybody's in the same, sort of in the same phase of knowledge. We bring them together in a 1 week hackathon when we get them to try out the knowledge they've learned. We have brain tumor segmentation data sets from previous challenges. We make that available to them. We have top performing codes that have been validated by the BRATS challenge. We give them those codes because the ones that are publicly available, we have the papers, we have the codes in GitHub. We give it to them. We get them to just play around with those codes, start to think about the gaps in those codes, start to think about what would happen if we give them brain MRIs from Africa, to work with those codes, start to see how to build their own code. So we spend a week just essentially hacking existing methods. And then once we know that they've tried those knowledge, they now can tangibly see what it means to code, how to develop these methods. We then get them to participate in the brain tumor segmentation challenge. So they now actually applying the knowledge and using it while they're still in the program. So they've gone from a process of coming in as a novice, getting some basic information in terms of knowledge, background basic knowledge. They have had some tangible, experiential, hands-on through an observership-like format, understanding of how to build these models. Now we tell them to now go ahead and build your own new models based on all this knowledge you've acquired. By the time they go through this BRATS challenge, which is like a whole 3 or 4 month process, they have the data sets, they've created the methods, they've done the validation, they've done the testing, they're now writing up the methods because they have to publish it as part of a conference paper. So they're getting transferable skills on how to write and publish. They come out as trainers. So they now are a little bit knowledgeable on how to build a deep learning method. If you can build it for brain tumor imaging, you can build it for practically anything else. So that's what we've done. The program have been running now since 2023. We're now in 2025. We've trained a combined total of over 700 or more participants. This is across 36 countries in Africa and around the world. We now have participants from Southeast Asia, participants from Latin America. We've created over 20 models combined. This year is going to be a little bit more because the teams have expanded. One thing I have to mention is that we don't train individuals, we train them as a team. So when they come into the program, they come into the program as a team. So we've already created a team that will be part of that BRATS challenge. So when they get to this point, you have the same team that have learned together, done the hackathon together, and now doing the challenge together. And when they leave, they become friends. A lot of them are now really good friends. They've worked for 6 months going through this training program together. And that's how we're creating this collaborative network. Because when they get out of the program, put them under the Spark community. And we now have a community of over 800 people across the continent and around the world that are now, doing a lot more beyond what we've trained them. Like I mentioned, the first time we run the Spark Academy, our team from South Africa came in second in the BRATS Africa Challenge. This is the team at the MICAI conference in Vancouver in 2023. This is the team, a whole new team of people. This is the conference that happened last year in Morocco. The MICAI conference happened to be the first time in Africa. We wanted to make sure that Africa had the presence. Some of these participants we had in 2023, like Friedmore, for example, came back, and Richard, for example, came back and trained a whole new set of people, which is how we're able to scale up. This is the team in the conference in MICAI. Conference this year, it's happening in South Korea later on in October. We're hoping to keep on growing the number of participants. These are the papers. This is just an example of the papers that have been published over the past 2 years from this methods. One of these methods is the segment anything model. So this is the SAM model. Think about it as ChatGPT for images. The idea here is that the students decided that they will essentially optimize this segment anything model to segment Africa data sets or to segment the brain tumor data sets from Africa a lot better than the foundational SAM model. And you can see that the model performed better, especially because they now understand some of the intricacies of the imaging data sets they're working with. They know it's low resolution. They understand that some of these patients are coming in with complex cases. Some of them are coming in with comorbidities, infectious disease being one of them. So they understood all of this stuff, which helped them optimize a model like SAM a lot better than the foundational model. All of the models and that have been developed at Spark are in our GitHub page. You can see the 2023 to 2024, including the ones that were not fully finished. The students claimed that they didn't like it, so they didn't actually, wanted to submit it for testing for the challenge. That's fine. The main goal for us was for them to learn how to do it, not to win challenges. Winning challenges is just or is just the icing on the cake. But all of these models are open source for people that want to just essentially use them to keep on learning how to train. And sorry, I see that there is an animation being off here. One thing I wanted to demonstrate here is that one of these students from Spark have essentially decided that they will solve one problem that is still lingering. A lot of these models were developed because we gave them access to Compute Canada. Compute Canada is a computational infrastructure that's available to faculty members in Canada. Me being a faculty member, I was able to make this available to Spark participants. But we know that this is not the case for everybody that is in the continent that want to learn or want to develop these methods. If you don't have a really good computational infrastructure, you're not able to do that, which is what one of the Spark participants faced. They wanted to keep on working on the models after Spark has ended, but they couldn't because they only had the CPU, which is the laptop. So they decided to think about solving this problem by developing what they call a lightweight brain tumor model based on a very common 3D unit model that they worked on during the Spark training program. And the idea here is that can this model run well on a CPU, which is the laptop? So they had to figure out how to optimize this model. And in the process, he created a tutorial for anybody. This is now a step-by-step guide to take anybody that is just a novice. This could be a clinician. Again, it could be an undergraduate student. It could be anybody that wants to try their hands on segmenting a brain tumor using a 3D unit model. And again, by doing that, you're gaining some knowledge. So he created this 4-step tutorial that essentially teaches them how to do data collection, prepare the images, process, load it, train it, all the way down to deployment. And I see that I was trying to animate that, but my animation is off. So this lightweight tutorial is actually in the Springer Nature Protocols. Springer has this new platform called Protocols where you can publish a protocol and it's publishable, so you have a DOI. And so we decided to take Ayomide's lightweight tutorial and publish it as a protocol, meaning that if somebody steps through it and each of the 4 phases has a video tutorial that takes you through what the section is, teaches you how to do it, and then you just do it on your computer setting, all the way down to deployment of the models. Essentially, it takes you from getting access to the brain tumor segmentation data set, running the model on your system, so setting it up on your computer or laptop on the CPU, doing the training, visualizing the output, what you've gotten, and trying to even move into what does it look like if you deploy this in a setting, so deploying this on Streamlit, just for them to see how this is done. So for clinicians, there's a lot of clinicians that have gone through this. We had about 54 so far people that have gone through this. We have a pre and post evaluation tool, and in general, most of them come out saying that the knowledge for AI has drastically improved just by stepping through this process. And you can go through this whole thing from start to finish in 4 hours on a standard laptop setting. So that's just one thing that came out of Spark. The other thing that I wanted to talk about, and this is again leaning towards those barriers, we talked about infrastructure, personnel, policy, is the ability for us to even have, and again, this applies to radiology, uh, ability to even get the data sets. One challenge that we had with doing this brain tumor segmentation challenge and getting data sets together is that there were no way for us to actually get access to archived images that were on their clinical systems, because some of them don't have what's called a picture archiving system, which is a PACS system. And so the PACS system is a system where we can actually archive in radiology information, and be able to also pull it back if we need to, for example, look at pre-post. So a patient goes for treatment, comes back to the imaging department, want to be able to pull up their previous images, look at it. Want to be able to share some of these images with clinicians. And also now that we want to do AI imaging research, we want to be able to go into this PACS system and look up the images that are there and essentially use them or archive them or access them for for AI method development. And most of them don't have a PACS system. So we are now developing a PACS system, which we call HASCI, but it's also lightweight because you have to meet one of the challenges. The challenges is also cloud computing. It's very expensive to cloud compute this imaging data sets. So we're now working on how we can use AI integration to archive these images, including maybe we can compress and uncompress the data sets for them to compress it when it's being archived, uncompress it when it's being retrieved. And a lot of other things we're trying to do to make sure that these type of solutions are available to them, because if you don't have the data set archived, you're not even able to build AI models. You're not even able to validate them to bring them back for deployment in the setting. And obviously, a lot of these AI tools are being deployed and co-deployed with a PACS system, for example. So this is what it looks like. It's still a works in progress. We're trying to implement some of these. You can see that 3D UNet model I talked about that Ayomide, one of the students from Spark, who is done actually building this PACS system. He's one of the key developers of this PACS system. He's now actually obviously trying to implement one of those 3D UNet models for brain tumor segmentation into the PACS system, so you can pull up these images from a patient. These are made-up names, by the way, and be able to now, as a clinician, come in within the same platform. You can do your reading. It's already automated, automatically segmented for you. It's automatically the brain tumor volumes have been quantified. So we're trying to now develop some of these solutions that will enable AI to be implemented well in a low resource setting. One last thing I want to point on before I start to summarize is that one of the challenges that is faced a lot with AI implementation, and I talked about infrastructure as being one of those key barriers, is the computational infrastructure. As you remember from our first slide, that AI divide is there. There's not a lot of data centers. Data centers are one thing. There's not a lot of high performance computing clusters or even computers that are available in the region. And even if they are available in the region, they tend to do like public health. So Excel number crunching, not medical imaging data sets that are very competition intensive. Like one MRI, one brain tumor MRI scan can go up to just about very close to half a gig. Yes, half a gig, right? And then you're not even talking about PET imaging, which is a lot more in terms of size. And so we are now trying to figure out how can we make this computational resources available from Spark, like I mentioned, because Spark runs in the summer. I'm able to use a Compute Canada cluster, We were able to use the University of Washington cluster this year, for example, in the summer. They only gave it to us for a month, which is not enough time to train a model. So we're trying to overcome some of these challenges and figure out how we can provide competition infrastructure in the continent for people to use to build AI models that can eventually be deployed into African healthcare settings. And so we're happy to partner, and I can't say who the partner is because this is going to be officially announced later on in October. But in October of this year, we're getting quite a lot of computing infrastructure, $200,000 worth of computing infrastructure that have been given to the lab. And we are going to take those computer infrastructure and make it publicly available for people in the continent to use. So we've created this Neuron platform. This Neuron platform will allow people to have access to the Soma Gateway. So I'm sorry, I'm a neuroscientist, a neuroimaging person. So everything I think about is in a neuro context. But we wanted to create this neuron as a way to not only give them access to infrastructure that they need to build the models, but also to give them mentorship. So a lot of people are coming in with very little understanding of radiology, MRI imaging, for example, very little understanding of the healthcare setting because there is a big gulf between science and clinic, especially in Africa, where some of these clinics are in, what some of these healthcare issues are in private centers that don't have any link to academia. So we want to be able to give them access to this cluster, but also mentorship as well as training around how to use this very well to solve the healthcare need. So this neuron infrastructure, we're going to pilot it first on people that have neurological imaging needs where they think that AI can, or deep learning or machine learning can solve those needs. They come to us with the need and the data, and then we provide them access to the cluster and give them mentorship. This is a very limited time. So 6 months is a good time to develop a model, assess that model, and then be able to now go ahead and keep building that model elsewhere or even start to move towards deployment. So we're going to we're going to pilot that and start this next in 2026. So keep an eye out for that. One list I wanted to mention is the need for you to be able to deploy AI well, especially in low resource setting, is there has to be a way for people to collaborate, understand what the AI is, build their own AI solutions, discuss that, evaluate that, and deploy it. Now, the reason why, like I mentioned to you at the very beginning on the onset, why we have some of these brain tumor segmentation softwares that are not available for people to use is because they use publicly available data sets. Those publicly available data sets came out of a conference, MICCAI, came out of a challenge, meaning that people came together in an environment where they're able to exchange ideas. So one thing we've been trying to do is to create this network, this a place for people to network, for people to exchange knowledge that are relevant to our healthcare needs. So we've created this workshop at MICCAI. This is the second year. Last year we called it MICCAI Meets Africa because it was the first time MICCAI is going to Africa. This year we've rebranded it quickly to be called Medical Image Computing and Resource Constrained Setting Workshop and Knowledge Interchange. And so it's running this year in the conference in MICCAI. We're creating similar spaces in similar other conferences. This is just one that ties on to this theme of that I've been talking about. We've also created this interchange session to allow early career scientists, early career clinicians, residents, fellows, people that have ideas but don't have the infrastructure, don't have the mentorship, don't have the personnel capacity to put those ideas to life. We've created this interchange session where they pitch the idea. This is like Dragons Den meets 3MT thesis. So they have about 3 minutes to pitch the idea to a jury that would then essentially be able to give them some tips on infrastructure or how to get access to infrastructure, provide them tips and mentorship on how to make sure the model they're developing is relevant, can work. So we have this essential environment. This is another way to make sure that we're training and retaining a lot of talent in the continent in these low resource settings to be able to make sure that when AI comes to being implemented, deployed is deployed well in these settings. So to round off, I think for implementation of AI across all settings, especially in resource constrained settings, I think there are three things that we all can work together on. One is to figure out how to optimize the infrastructure we have. So this is that big issue around the barrier. And we can do that well by just using clinical data sets, learning from those data sets, using those data sets to optimize our own healthcare environment, training a lot of people within that particular environment to make use of these infrastructure that they have and optimize those infrastructure and actually build those AI models, implement them well, and make sure that they work within a collaborative environment because that's how they support each other. That's how they're able to even get more funding. That's how they're able to keep on implementing and making this AI implementation work well. I'm going to stop here. I thank you all for your time, and I'm happy to take any questions that you have.
Thank you, Dr. Aduna, for this insightful presentation. We have a few questions from the attendees. So,
Sure. I'm scrolling through all of them and see how much I can. What are the plans in the near future to get enough? Oh, yes. So, Alfred, the good news is that when we started doing this work back in 2019, when I started, and one thing I glossed over in my presentation is that a lot of this work was done through the Consortium for Advancement of MRI Education and Research in Africa. Camera, you can see that on the bottom of my screen that you see the logo and then the website is there. When we started the work with Camera, we did a needs assessment survey back in 2020. At that particular time, there were not that many MRI scanners, but we could see that they're coming, meaning that the environment to install the scanners, one of them being power issues, have been sort of figured out. The vendors have figured out how to make some of these scanners run well within our low power setting, but also, like I said, they're a little bit lower field, or in the case of PET CT, there's certain different or cyclotrons, there's certain different cyclotrons that are not well recommended for the African setting. Long story short is that there are a lot more scanners coming. So I just came back from Nigeria 3 days ago. I was across the whole continent, and while I was there, a 3 Tesla scanner was installed in Abuja recently. While I was there, 3 new scanners were installed. So the scanners are coming. They're not enough, but they are actually now slowly making their way into Africa. There's been a lot of private-public partnership. For example, GE has partnered with the government of Kenya, partnered with the government of Nigeria. There's a lot of these partnerships now happening where they're helping make sure that the funding scheme is there to allow centers to buy the scanners. So they come in. Our biggest challenge is now the people to run them. A lot of these centers are still run by people from Southeast Asia. For example, the PET centers in Africa, most of them are run by Bangladeshi or Indian people from India and Bangladesh. There's very little people that are trained to do PET imaging in Africa or even MRI in Africa. From the imaging to the interpretation to the being able to even maintain so the biomedical engineers. So training of people is now a big challenge in general. What level skills needed to implement AI? The level skills needed to implement AI is motivation. That's what I tell everybody, motivation. A lot of people that we trained from Spark, for example, the clinicians didn't even know what deep learning is when they got into our program. They left being experts in the sense that they are now running their own teams or having students working with them now. So for us, it's motivation and commitment. AI has gone to the point where anybody can learn it. A lot of these models are now very modular, very block design. So the concept it's there. We use a conceptual approach to teach. We teach with a use case, very hands-on, and so anybody can learn AI. The level of skill needed is just motivation. Let me see. Attendance survey check permission. Okay. Africa is a great job. However, the training schedule in attracting wild personnel across Africa. Africa is a great job. However, is the training schedule in attracting wild personnel across Africa open to the public? Yes, it is. So we are now we're going to launch a pitch. So essentially every year we open up a call for interest in participating in AFNIR. Essentially, that call is open to anybody that wants to participate. We have a process. We go from ethics, and I probably should have put that in the slide. We go from ethics, a call for interest. We do a quick 1 hour webinar just to get people that have signed up an idea of how AFNIR works. We then help them work on the ethics, local ethics, have an ethics template, which is what we're actually doing right now for the next call. Work on the ethics template. Then we train them on how to process the data, annotate the data themselves, and then we do it together because the whole idea is not to curate the data set. The whole idea is also make sure that people are aware and able to set up their own local data set, to do their own local AI development, do their own local AI implementation. So we use this as a process to do that. So yes, it is open to the public. I would say that you follow us on our website, Camera website. That's where you can get all this information. Let me just see if I could quickly find the website here. And our Twitter, and you can find our Twitter and can I do everyone? I don't know. I only have hosts and panelists, so I'm going to put this in the host and panelist link, and then the host and panelists can put this for everyone to see. So the link is there, the Camera website is there, and we will, what we do essentially is that if you go follow us, we will have all these calls open and available for everyone to participate. Quickly for time, let me see what else is there for question. Quick question. Beyond detection, how is AI being integrated into treatment planning, for example, in predicting tumor growth? So I am more in the medical imaging side. I can only speak so much about tumor treatment planning. I don't know much about that because I'm not on the oncologist side, but there is obviously AI models that have been developed for treatment planning. One of them is using the BRATS data set. So there is the BRATS has a couple of sub-challenges now that are running. One of them is called BRATS, I forget the acronym now. Essentially, they are providing pre and post therapy data sets. One of the tasks is to be able to improve treatment planning and predicting not tumor growth patterns, but essentially being able to make sure that they can at least predict the tumor volume between pre and post therapy, something like that. So some of those AI methods are there. What are current limitations? Limitations always start with data. If you don't have the data, you don't have nothing to train. So that's one of the biggest limitations. So all the limitations I talked about applies very well to treatment planning, applies to any healthcare setting where AI is going to be implemented. If you don't have the infrastructure, if you don't have the personnel, if you don't have the policy, you don't have anything going on. So it's the same application. Have you integrated medical imaging AI models with other data sets, pathology? So pathology is something we're working on right now. Where there is a project that Maruf Adewale, who is one of the students that came out of the lab, now a postdoc at Penn, is putting together a long CT and pathology data sets for lung cancer. So that's ongoing. We haven't integrated any of these. A lot of these models cannot be integrated in the African setting. Example I gave you is one example of that because a lot of them do not have the understanding of the nuances that come with the African data sets, including pathology. So you have to include those in the training in order to deploy them very well. So we are essentially in the beginning of this integration and deployment because we're making sure that the data sets are actually being part of the training and actually have been validated for our setting and our use case. Can we use CT images to train? Yes, we can use CT images to train deep learning. I just showed the MRI because of the time sake. I focused on one particular thing. You can use CT. There's lots of CT. During my PhD, I essentially created a model that will essentially make synthetic MRI from CT. The application for that was for PET imaging because I did my training on a PET MRI scanner. PET MRI scanner is a scanner that has a PET and MRI integrated. So there was no CT to do attenuation correction for PET. And so the idea was to take synthetic MRIs, to take MRIs and turn them into CTs that will allow us to do PET attenuation and synthetic CT. So yes. And obviously we had to evaluate that on real CTs. People are actually going the opposite way now, taking CT MRIs and taking CT images and turn them into MRI for treatment planning for radiation therapy because some of them don't have MRI Linacs. So that kind of stuff is ongoing. What are some ways that radionuclides can be used? Yes, okay. For radionuclides, so that's radiation, for radio tracers. Again, I'm actually a PET MRI physicist, so I have a whole lab that does PET research. And one of the things we're trying to do is low dose PET, which is essentially trying to figure out ways to denoise PET images well so that we can enhance the signal and be able to lower the dose because we now have good enough contrast, so good enough count density to work with. So we have a whole paper on low dose PET, and that's actually becoming quite useful now in African settings. So when I was at the PET center in Nigeria last week, they were actually doing low dose PET by necessity. Necessity because the PET CT in Lagos is the only PET CT in the whole of West Africa. So they have patients. When I was there, there's a patient that flew in from Ghana. The patients there, So you have this huge patient population. You have a cyclotron that is so small that only should be making 6 doses, but they're taking that 6 dose and splitting it into 20 to scan 20 people. So you already are doing low dose PET out of necessity. And also because they have so many patients, they cannot scan a typical standard protocol of 20 minutes for a whole body scan for oncology. This is obviously oncology place, is a cancer clinic. So they're doing 5-minute scans with 1/3 of the dose. So this is where AI has to now come in and help them enhance the quality of the images they have. So we're talking with them right now to actually get that going in that center. So I think I've answered all the questions. I'm happy to answer more. You can reach out to me. Again, I put the link for the camera there, which is where a lot of this work is done. The link for our lab in Lagos, I'll put that there also. So you can also see some of the work we're doing in the lab. We're more than happy to collaborate with anybody that wants to collaborate with us. If you're in Nigeria or in Africa, you want to stop by the lab in Lagos, more than happy to have you around. The more the merrier. Once we have Neuron up and running, if you're interested in using Neuron for any application, including in radiation therapy, radionuclide, or PET, if you're in Egypt, that's also fine. The lab is called My Lab for a reason because it's our lab, it's everybody's lab, it's an open lab. We have a lot of participants. Like I said, we run Spark from the lab. So we've been running Spark from this lab, and we have a lot of people that come in from around the world to use the data sets that we have, and obviously eventually the infrastructure that we have. So I'm going to end here. I'm a little bit jet lagged, so if I'm talking very fast, it's because
Okay.
I'm still sort of switching back to my North American time zone.
Thank you, Dr. Luna. We actually have some more questions from like the Q&A.
Oh, okay,
That
okay. Sorry, let me go into the Q&A. Yes, yes. Can we train a model to
yeah.
see images? I think I've answered that question about that. What are the plans to improve the capacity for AI in Africa? Okay, so Mishak, I think that what I've presented so far is a really nice plan, and it is already improving capacity for AI in Africa. Because when we started this program in 2023, when we started Spark in 2023, for example, um, there were no AI, at least in medical imaging, let's just say in healthcare, papers, not a lot, not even any. So far, since we've started that, our participants, we've trained about 700 and something. I don't have the numbers off my head in the space of 3 years, counting the ones from 2025. We've had them participate in Diaba, which is a AI conference in Africa. We've had them participate in conferences in Rwanda, in Kenya, in Ghana. This is just them doing something beyond what they were trained to do. So people are going into malaria detection with AI. We didn't train them to do that. That's what they're doing. We have people doing pathology work as well for breast cancer. This is obviously using open data sets. So we are improving AI capacity right now. The plan is there, and the plan is very simple. It's to train people that are in Africa to learn how to build AI models that are relevant to Africa and within the African setting, to be able to optimize the infrastructure they have. The health infrastructure they have includes essentially how they protocol patients, for example. That's part of the infrastructure. To optimize that infrastructure with AI and to be able to continue to work in a collaborative network. That's our plan, and that's how we address AI capacity in Africa. So that's actually working, and it's there. What are some of the AI implementation best practices? Yeah, so some of the implementation best practices, I think the first best practice is you have to be able to make sure that the user, so they have to take this user-centered design for AI implementation. And this is very applicable, especially for resource-constrained settings, because if the person developing the model that will eventually be implemented does not understand the user and the use cases and the use environment, they're going to develop not a solution, but a trade-off. So what I mean by that is, if you don't understand the problem very well, this is a famous saying by Gilbert Chesterton, who is a 18th century old person from England, that this is a very good saying, and it stuck in my head when I was a student, is that if you don't understand the problem very well, you're not really going to create solutions. It's not creating solutions are actually quite easy. Our biggest challenge is actually taking a step back and understanding the problems. If you don't understand the problem very well, you're really not going to create good solutions. What you're going to create is a trade-off, meaning that you might end up creating what's a solution, but end up becoming a problem later on. So the best practice for AI implementation is to first of all use a user-centered design. By using a user-centered design, you have to actually understand the user. So you have to include the users, which is in case of radiology, diagnostic imaging is your question. Make sure the radiologists actually aware, part of the design, part of the implementation, part of the evaluation, because they're the ones that are going to use this. If you create a tool that have no meaningful use for them, they will not use it. And that's happening a lot in the continent, a lot in the continent. How is the patient data protected during AI trained deployment? Yes. So if you remember the AFNIR wheel, the first thing we had at the beginning of the wheel is ethics and data protection. So we have now created a ethics template that we use even for private centers. We actually are helping private practices set up ethics boards within their private practice. That's happened during our first deployment, during our first branch challenge in 2023. So we are now training them on how to have ethics applications within their private setting. So we don't want to have the ethics approved here in Canada and then list them as a center. We're wanting to make sure that they're aware of what's happening to their data sets by them setting up an ethics process, going through the ethics protocol. They actually have a sense of what is happening to the data set, including from who is accessing the data, what it's going to be used for, what data set accessing. Is it data sets from 2021 to 2024 that's archived? So all of that stuff is actually part of data protection. We don't think about that because they are now stewardess and they are now actually what will I call it? They're now part and parcel of what is being done to the data and what is going to be done even after the data leaves the institution. That's one. Second is we have data use templates. So these are data use agreements that we've set up so that the clinics themselves are signing up to this data use agreement. Those data use agreements are on. If you go to download the BRATS data set that's out there, the BRATS Africa data set, there's a data use agreement that's there. So that's one way of data protection. And we also are now, not now, we are, and this is one reason why AFNIR is not in every country, is that we are slowly trying to make sure that the countries that we're getting into are the countries that already have some amount of data protection laws out there. And that's Nigeria, Ghana, Kenya, Tanzania, and Uganda. That's where we are right now. At least in Sub-Saharan Africa, those are the places that have solid, I shouldn't say solid because not most of them are not solid, but they have useful, some defined data protection laws that we are comfortable working with, especially because we don't want to have these data sets leak across borders. They are leaving anyways. So first of all, the data is leaving because in Africa, most African centers, so I'm going to use this broadly, radiology is in private practices, overwhelmingly private practices. And most of the images are not read by radiologists based in Nigeria. They're read by teleradiology. So most of these radiology practices have a teleradiology service that they subscribe to. These teleradiology services are now bringing AI into teleradiology. So a lot of these radiologists are based in India. They're based in Southeast Asia. Some of them are Africans based in the West that are now have a teleradiology service that they're now providing to imaging centers in Africa. And so the data is leaving anyways, it's leaving to this teleradiology service. So we're trying to make sure that we are at least using some mechanisms to protect, provide privacy, provide some protection around the data. But also as Africans, we have to be very careful that we don't overprotect the data. Because if we overprotect the data, then we will not be able to make those data sets available to now train models. Remember, our data sets, it's always going to be few and far in between. So if you protect the few that we have, we're not going to be able to make them available to now build robust, generalizable methods. Okay, how do AI systems handle missing and complete data sets? So we have, as part of the BRATS data challenge, we have this missing modality challenge that's running. And so that's one thing we're trying to do is to see how we can use AI to start to synthesize maybe missing volumes. So for example, if they don't have diffusion weighted imaging, can we synthesize that from T1, T2, and some of this other stuff? So we're trying to do that now. So I think that kind of answers all the questions. I don't know if there's any more questions, and I'm not sure if I'm out of time already. So I'll leave it at that and hand it back to you. Well, I'm not sure if it's Dr. Ungwa that's moderating, but whoever that's moderating, I'll hand it back to you.
All right. Thanks so much. Thanks so much, Oduna, for this wonderful lecture. I think that we learned a lot from you and your experiences. And I think if there are any additional questions, we will definitely be reaching out to you, to tap from your experience. And I think you're really a trailblazer in being able to help with implementation, especially in Sub-Saharan Africa. So, thank you so much for that wonderful lecture. And for our participants, thank you so much for joining today. We do have one more lecture next week, and we look forward to getting together next week again. Bye.
Thank you so much. Thank you, everyone.
Yes, have a great week. Yes.
Yeah. Bye.